Okay, in this video, I'm going to overview the background sections for Lab 5. Let's start with Section A on the magnitude system. In this lab, you're going to measure brightnesses and use luminosities to calculate distances to a variety of objects. Now, astronomers measure brightness and luminosity in a peculiar kind of way, based on the ancient Greek system for doing this called the magnitude system. Let's start with brightnesses. When an astronomer measures an object's brightness, we're measuring a quantity called its apparent magnitude, though we'll often refer to this simply as its magnitude for short. This is a backwards powers of 10 system, in which small numbers and negative numbers correspond to brighter objects, such as the sun here with a magnitude of -26, or the full moon here with a magnitude of -12, and where large numbers correspond to fainter objects, such as Pluto here with a magnitude of 15. So let's practice this. I want you to go to Afterglow and load in this image. You'll find it in the sample directory under Astro 101 Lab, Lab 5, CD47. Then I want you to watch this tutorial on how to measure an uncalibrated apparent magnitude. Once you've done that, go ahead and measure the uncalibrated apparent magnitude of star A. You can insert that value here. Now, it's uncalibrated because if we were to go back and take this image again and remeasure star A, we'll come up with a different value, depending on how much atmosphere we're looking through this time versus last time, whether we're looking through a thin layer of clouds this time versus last time, or if this time we use a different telescope and camera, which may allow more light or less light through. So we'll come up with a different value. And the way we correct for this is by using a reference star. This is a star of known apparent magnitude. And you use it as follows. Go ahead and measure the uncalibrated apparent magnitude of the reference star, same as you did for star A, and put that here. Now, since this is a reference star, we know what apparent magnitude it should be. It's 12.02. So you can then calculate a correction constant. The correction constant is the true magnitude of your reference star, in this case 12.02, minus the uncalibrated apparent magnitude that you just measured. Once you have that correction constant, you can use it to correct any uncalibrated apparent magnitude in the field. So let's use it to correct that of star A. Take your uncalibrated apparent magnitude for star A, add the correction constant, and then you'll have the calibrated apparent magnitude for star A, and you can put that here. Now, the true magnitude of star A is 13.75. And if you did all this correctly, you should be within a few hundredths of a magnitude of that value. Okay, so that was brightnesses. Next, we need to talk about luminosities. So let's go to Section B, standard candles. So there's a difference between brightness and luminosity. Luminosity is intrinsic to the object. It's the same, whether the object is close to you or far away. For example, take a light bulb. Its luminosity is measured in watts. A 60-watt light bulb is always 60 watts, whether it's close to you or far away. But its brightness does, of course, depend upon its distance away. So there's a relationship between brightness, luminosity, and distance, and you may have seen it before. Here it is. An object's brightness is equal to its luminosity divided by 4 pi distance squared. And you can solve this for distance, and you get distance equals the square root of the quantity luminosity divided by 4 pi brightness. So if you knew an object's luminosity, all you would have to do is measure its brightness, which we learned how to do in the previous section, and you could then calculate its distance away. However, for most objects, we don't know their luminosity. You can't see luminosity. You can see brightness, but you can't see luminosity. For example, this observer sees stars A and B as having the same brightness, but that does not mean they have the same luminosity. In this case, star A is lower luminosity and closer in, and star B is higher luminosity and farther away. However, there are certain classes of objects out there where we know their luminosities, and we call these standard candles. If you can identify an object as belonging to one of these special classes, you know its luminosity, so then all you have to do is measure its brightness, which is one of the easiest things to do in astronomy, and then you can calculate its distance. In this way, we can measure distances much farther out than we could with the parallax technique in Lab 4. Now, astronomers, as we discussed before, measure brightnesses and luminosities in the magnitude system. So instead of using this equation, we will use this equation. It's the same equation, just written in terms of magnitudes. Here, little m is apparent magnitude. It's effectively the brightness, and we learned how to measure that in the previous section. Capital M is something we call absolute magnitude, and it is the counterpart of luminosity. So again, the way this works is if we can identify an object as belonging to one of these special classes as being a standard candle, we know its luminosity, or in other words, we know its absolute magnitude, capital M. Then all we have to do is measure its apparent magnitude, little m, and we can calculate its distance away. Now, in this lab, we're going to do this for 3 types of standard candles, 2 variable stars and 1 exploding star, also called a supernova. Let's start with the variable stars in section C. These are stars with outer layers that expand and contract over and over and over. As they expand, they go brighter, and as they contract, they grow fainter. Now, there are all sorts of different types of variable stars. We're going to focus on 2 of them, RR Lyrae and Cepheids. RR Lyrae vary with a period that's less than 1 day. Cepheids, on the other hand, vary with periods that are longer than 1 day and can be as much as a few months in duration. Let's start with the RR Lyrae. We found some RR Lyrae nearby, close enough that we could measure their distance with parallax. We also measured their average brightness, their average apparent magnitude, and that allowed us to calculate their average luminosity, their average absolute magnitude. And we learned they all have approximately the same average absolute magnitude, 0.75. Some are a little bit brighter, some are a little bit fainter, but overall, they're all about 0.75. We can then use that information to determine the distances to RR Lyrae that are much farther away. We find a variable star, and its period is less than 1 day, telling us it's an RR Lyrae. We then know its average absolute magnitude. And all we have to do is measure its average apparent magnitude. Then using the equations above, we can calculate its distance away. Same deal with the Cepheids. We found some relatively nearby, close enough that we can measure their distances with parallax. We then measured their average apparent magnitude, their average brightnesses, and calculated their average absolute magnitude, their average luminosities. And what we found is that the average luminosity of Cepheids does vary from Cepheid to Cepheid, but in a predictable way as a function of their period, as you can see in this plot here, and as is described by this equation here. So we can use this information to determine distances to Cepheids much farther away. If we find a variable star too far away to measure with the parallax technique, and we measure its period to be longer than 1 day, telling us it's a Cepheid, we can then plug that period into this equation, and we then know its average absolute magnitude, its average luminosity. Then all we have to do is measure its average apparent magnitude, its average brightness, and we can calculate its distance away. All right. Let's go to section D. This is our final standard candle. This is not a variable star, but a type of exploding star called a type 1a supernova explosion. It's a special kind of supernova where you have two stars in close proximity. One goes through its life cycle, sheds its outer layers, and becomes something we call a white dwarf. The other star eventually nears the end of its life cycle. It becomes a giant star, and since it's in close proximity to the white dwarf, when it does this, mass begins to flow from the giant star onto the white dwarf. And the white dwarf slowly becomes more and more and more massive until it becomes 1.4 times the mass of our sun. That's the mass at which a white dwarf can no longer hold itself up, and it begins to collapse. And as it collapses, it heats up, and pretty quickly, it achieves the carbon ignition temperature, 6 times 10 to the 8 Kelvin. Since the white dwarf is made primarily of carbon, as soon as it hits this temperature, all that carbon ignites and the star blows up. And that's why this type of supernova explosion is a standard candle, because you're always blowing up the exact same amount of fuel. So it will achieve the same peak luminosity. Now, not all supernovae are standard candles, only the type 1As. So if you find a supernova explosion out there, first you need to be able to identify it as a type 1A. Type 1As peak early, within a few weeks, and then fade away. The other types of supernova explosions peak and then plateau for many months before fading away. So this works as before. We found some type 1A supernovae in nearby galaxies, close enough that we can measure the distance to these galaxies and hence to these supernovae using the Cepheid technique from the previous section. Then we measured their peak apparent magnitudes, their peak brightnesses, and could therefore calculate their peak absolute magnitudes, their peak luminosities. We found that all the type 1A had the same peak luminosity, peak absolute magnitude, and it's given by negative 19.3. Given this, whenever we find a type 1A farther out, farther than we can measure the distance to it using the Cepheid technique, all we then have to do is measure the peak apparent magnitude. Given that and this peak absolute magnitude, we can calculate the distance to these supernovae and hence distances to galaxies much, much farther away. Okay, that's it for this video.